Okay, so we're going to be looking at antiderivatives and indefinite intervals. So what is an antiderivative? So an antiderivative of a function f is another function g whose derivative is f. G is an antiderivative of f when g prime is equal to f. So we're going to be going backwards now. All right, so the most common way to express the relationship between a function and its antiderivative is with an integral symbol with no limits of integration. So we're going to look at this thing right here. Using the same statement as above, let's see, so this is the integral symbol. The integration of f of x dx is equal to g of x plus c, where c is some constant. So in other words, this right here is the antiderivative, okay, of f. The whole thing, this integration symbol. And so that's what you get with g. And what's going to happen is you're going to get a bunch of a nested family. So a bunch of g could be anything I want it to be, and then the constants is what changing. And if you remember what a constant does to a graph is a translation up and down. So you're just going to get a bunch of nested family differing only by a vertical translation. We need to add a constant because a function can have many antiderivatives, each differed by a constant. That's what I just stated. Here are some functions. Let's take a look at these things over here. Kind of walk you through this. X squared plus 3, x squared minus the square root of 5. All of these are antiderivatives of 2x because if I take the derivative of all of those, they will all equal 2x. So this is what I was referring to up here. Okay, taking the derivative of these things, they can all differ by a constant, and I will end up with the same derivative for all of those. Okay, so that means we can have more than one antiderivative of a function like this. This symbol right here, this integration symbol of f of x dx, can be read as the integral of f of x dx or the indefinite integral of f of x dx. The best way, though, because it conveys its meaning, is to call it the antiderivative of f of x. Okay, think of it as an antiderivative, and it helps with a lot of questions that come up in a little bit. Some words and symbols to know. G of x is an antiderivative of f of x when the derivative of g equals f of x. Okay, and so you want to get used to this notation in this conversation because otherwise you're going to get confused with some questions. This right here, x to the fourth over 4, is an antiderivative of x to the third because if I take the derivative of this, I'll get x to the third. Here's this symbol. Okay, we're taking the integration of g prime of x dx. So the antiderivative of g prime is g of x plus c. Okay, because if I take the derivative of this, I'm going to get g prime. That's pretty much what it means. So here's one that's a little bit more advanced antiderivative look here. But if I take the antiderivative of this, I'm going to get that. Or if I take the derivative of this, I'm going to get that. So think about it. The derivative of e raised to the x squared is e to the x squared times the derivative of the top, the exponent, which is 2x, and then the derivative of constant is 0. We're going to do problems like this a little bit later once we learn our rules a little bit more in detail. The derivative of h is f of x. So this is another way they can say it. The derivative of h is f of x. So the antiderivative of f of x is h. Once you have the wording, try and refer to it as the notation so you can see and think of it differently. H is the antiderivative of f of x, which means if I take the h is the derivative of h is f. The derivative of h is f. So the antiderivative of f is h. So this is the symbol notation for it. Okay? Again, this is just a new notation for us. We have a bunch of rules over here. The rules are now in play. So they are connected and similar and related to the derivative rule. So as long as you know the derivative rules, you can help you find the antiderivative rule. This is the power rule right here. So in this case, we take the derivative of this, we're going to take what? We take the exponent, multiply it out front, and then lower the exponent by 1, provided n is not equal to -1. This side over here is what? How do I get to that? Well, same thing. If I take the derivative of this thing, take the 1 plus n out front, it's going to reduce with that, and then lower the power by 1, and it gives me the x to the n. So you can see a comparison of each of these things as we go across. You're going to want to memorize all of these rules and get really, really good at them. So you have them on that note list that I gave you. These are the integration rules. So you don't need to copy them from here. You already have them. Put them on flashcards so you have them down. It has to be automatic. These are not all the rules that you're going to need, but this is the first list. Okay? Okay? There's a ton of integration rules. You're not going to memorize them all. You're just going to stick with the basic ones, which are these right here. Okay? And so let's do some practice. Do some practice problems over here. Now, I'm going to be using those rules that you just saw to answer some of these questions over here. So let's go ahead and take a look. Find a function whose derivative is that. Okay? So think about this. What does it look like? Again, use your derivatives to help you see it. Okay? And I don't have that one on here, but look closely at it and start noticing the pattern that you see from this one. This right here is simply the product rule. Okay? And they have it, this one's written a little bit backwards, but you should still recognize that I have a derivative of one and a regular of another. So here's like be g first times derivative of the second plus the second times derivative of the first, kind of a deal. But for the most part, this is just f of x times g of x. If I take the derivative of this, I'm going to get that. Okay? So look at this one right here. As we look at this stuff, we got to look at each individual piece here. Okay? So what would be the antiderivative of this thing right here? And so take it one piece at a time. So how do I get a constant by itself? So think about derivatives. What do I take the derivative of to get this constant 5? Well, there has to be an x involved. So it is 5x. If I take the derivative of that, do I get the 5? Yes. How do I get a 2x? Think about functions that if I take the derivative, I'm going to get a 2x. Well, go backwards with your derivative rule. This has to go back up on top, right? And so this one's coming from x squared. And then double check it. Take the derivative of that. Do I get 2x? Yes. Over here, I'm at 3 times this quantity right here. So when I take the derivative and there's a constant involved, it just carries on throughout the problem. So the 3 is going to carry on through this problem also. So constants can just be carried through. And then what is the antiderivative of the cosine? So what function do I take the derivative of that gives me the cosine? Sine. And if I take the derivative of this, do I get that quantity there? And the answer is yes, I do. And so this is a process you can do. You're looking for what I have and then how I'm going to go about and get it. So look at what I have. E to the x's, e to the powers are always its own derivative. So something that's going to have this as a derivative has to have that in it. So we know that's part of it. Well, what happens if then what is this part? Where does this come from? Well, we know if I take the derivative of this, it's itself. And then I have to take the derivative of this, that's the chain rule. And the derivative of this is that. So that is the only answer right there. So let's take a look at this one. Okay. What do I take the derivative of to get secant squared? And you can see clearly that we have right here, correct? So the antiderivative of the secant squared is simply the tangent. Okay? So these questions down here are asking the same thing. This was, find a function whose derivative is this, or I can ask, what is the antiderivative of this? In other words, what's the name of a function that I can take the derivative of to get this quantity that's in the parentheses right here? And so since we did one very similar to it up here, take one piece at a time, start with this one. The 9, what would be the antiderivative of 9? Well, it'd be 9x. Okay? And then what can I take the derivative to get this quantity? Well, I see a 3 here and then a 2. So literally, what am I going to do? I'm going to raise this power by 1 and then divide by the raised exponent, which is this one right here. This is for power rules. Raise the power 1, divide by the raised exponent. And so this is simply going to be x to the third. Take the derivative of it just to make sure. Take the 3, multiply it out in front, lower this by 1, gives me that quantity right there. Now this has a constant and then the cosine, so very similar to what this one was up here. So we just carry the constant through, and then antiderivative of this would be the sine of x. Now, because it is in this format as an antiderivative like this, we have to put the plus c. Okay? This one asks a different question. Is find a function, not all of them. This one is asking us to find the whole family. This is the whole family of functions that relates to this one right here. So that's the plus the constant. Because the derivative of a constant is 0, so it is not shown up here. So we have to anticipate that it might be there. Okay? Same thing with this one. This has a constant. Look for a rule that might closely resemble this. Okay? What can I take the derivative of to get this? Now, when I see fractions like this and square roots and things squared, I automatically start thinking about the inverse functions. Okay? The inverse functions. Now, again, there's more than just these right here. Remember, there was one for each one, so you're going to make sure you add to this. But if we look at it, the square root of 1 minus x squared, that's this one right here. But we'll notice that there's only a 1 on top, and I had a 2. So that just means it's the constant. Okay? Just like this 9 was a constant, this square root of 7 was a constant. So this is just a constant. So it's just going to carry through. It's still going to be a 2. And then it's going to be the arc sine of x plus a constant. Okay? Until you get better at some of your rules, again, when I see these things with squares in the bottom, I'm drawn to think about, is this one of those inverse trig function things? And we look over here, and I see a 1 over 1 plus x squared, 1 plus t squared. So yes, everything here is t, and that's just a constant again. So this thing is going to be 2, and then it's going to be the arc tangent of t for that one. Okay? And so what about this one? What is this going to be? Well, you need to keep in mind for these fractions like this, I can take, this is just a number in here. So remember, t over 5 is just 1/5 times t. So I can take the 5 as 1/5 as a constant and know that that's just going to come along for the ride. And then what number can I take the derivative of to get just this? Okay, so what is that going to be? And if you're not sure, we can use this rule right here. So I have t to the 1, t to the 1. So I'm going to raise the power 1, so it's going to be a t squared, but then I have to divide by that raised exponent, which is 2. So this t part becomes t squared over 2. And then plus this is just a constant. So just like the 9, it's just going to get an extra letter. So it'd be like t to the 0. So you raise the power 1, becomes t to the 1 divided by 1. So this is just going to be pi times t, and then plus a constant. And then you can clean this up to be t squared over 10. Okay? This one down here, find a function h such that the derivative of that is this quantity here. So I'm literally just asking you to do what is the antiderivative of h prime of x dx. And I want that to be h, okay, the antiderivative of this. And so what is secant squared? So we just go and look at this stuff. That's the tangent. And secant tangent, right? That's secant. This one has a 3x here. This one does not. So this one is pretty straightforward. And we'll end up here with a tangent of x. Okay. Now what is this? Well, the derivative of a secant is secant tangent. If there was a number in here, then by chain rule, I'm going to have to take the derivative of the inside also. And our inside is a 3x. So the derivative of 3x is that 3 right there. So you can see that that's going to help us with this. And so this over here just simply becomes the secant of 3x. And you should always pause and check your work. The derivative of the secant is secant tangent times the derivative of this, which is 3. And there it is. And then the last thing here is we want to find plus c. Okay? And this represents all of them. So we'll practice more of these together. And it's all about memorizing those rules. So the sooner you get that done, the better. And we'll do more problems in class.